And we're back. So in the last video, we got to the point where we implemented the finite difference equation for a string. So implementing the wave equation using finite difference approximation and then applying that to a string. And then we got to the point where we identified a maximum step size. So as long as our time step size is smaller than this value, then we shouldn't have any problems with stability. And then we got to the point where we simulated the first 10 steps of the string, which corresponds to something like 0.7 seconds worth of time. In this video, we're going to be going one step further and actually trying to animate this. I don't know if you've seen some of my other videos. It's actually quite nice to always visualize what's happening. So it's good to see a plot with many different lines, but if you can actually see it animated, that's really good. Another thing to note actually that I would say is that obviously the wave equation by itself I don't want to say it's quite a simple equation, but it looks quite simple, but when just looking at it, you don't really know what's happening. There's no obvious like shape to it or what happens given this initial input. So I think actually being able to see it in something like this is actually really nice. So let's go ahead and start animating. The first thing to do, if you want to animate using matplotlib, it's really easy. We take a import, so for matplotlib.animation, import func animation, so function animation, so animates a function over and over again and plots the result. So we've already created a plot, which is here. So fig.x equals plot.subplot. So we have our plot. So let's just remove that. We'll create our string first, our string object. We'll then go ahead and plot it. So that's just the first frame, basically before any time step. For this function animation, we need to do something like this. I'll just copy some code over. Basically what it does, it takes a figure, which we've created, and it calls a function update. So let's create a function update. So this is what's going to happen every time an animator is ready for a new frame. It calls this function. Let's just pass for now. There's also an initialization function if we wanted. This is a function that's called before the first frame is updated. So I'm going to do 1,000 frames, arbitrary at the minute. And then we also want an interval. So an interval is a time in milliseconds between each frame. So I've created a variable here called FPS. Let's go ahead and create up here. So FPS equals 10. So I want to plot at 10 FPS. Every 10 times a second, I want it to update the plot. Okay, pretty easy. What we need to do now is we need to think what we're trying to update. So we're trying to update the position of the string. So every time you want to update the string in this update function, we need to call string.increment. And we're going to increment it by dt. Okay. We then need to return something that will change. So in this case, we're going to return a line, and the line object is given by the plot object. So when you do a fig.x, a figure and an axis, so axis belongs inside the figure. When you go ahead and plot something, it returns a line object. So this is that line here. And that line is basically a container for all the data and all the different styles that that particular plot has. So when you actually call this plot, it plots a line. So this line object now has access to all that, all those variables, all that data. So what we need to do now is every time this plot wants to update, it's going to call this update function. What on earth's going on here? It wants to call this update function. So we're going to update it by incrementing delta t. We then need to change the data associated with that line. So we can do line.set y data. And then we can give it the new y data. And remember that when we call the increment function, the internal state of the y variable for the string is incremented by delta t. So we can do the same. Okay, return that, and then we have to return it. We have to tell the function animator that the line object has changed, so it knows to animate it. And we run that, you'll see something very interesting. It disappears because line is not defined. Let's have a look. Line equals, always remember your equal signs. Must return a sequence of artists. Let's just pass a line here. We don't really need the initialization function. Yeah. Must return a sequence of artist objects. Ooh, it's now working. We can see that the string is indeed being animated. But you see, we have a small problem here, is that the limits of the plot do not change. And if you watched my previous videos, you know that getting it to change every single frame is actually quite slow and can make it quite jerky. But we've got the advantage here, is that we know that the string displacement should never exceed the initial displacement. So it's quite hard on the, especially when just say plucking a string, if you were to release it, you wouldn't tend to get the string displacement to actually be above that, to go any higher than it initially was. So we can do that here. We can say ax.set underscore whilein, and we can say let's just go from 1.1 times d naught, or minus 1.1 times d naught. Remember, d naught was this initial displacement. And then we can go from to 1.1 times d naught. And that should mean that we have our permanent limits. Okay, which is very nice. And it's going a bit slow for my liking, so let's see what happens if we just increase the speed. You see, it doesn't actually go any faster. And that's because even though we've increased the speed, we're still plotting every single time we increment dt. What we would really like is if there was a way that we could say, okay, let's try and plot in real time. So let's try and actually say 10 times a second, which is what the plot's putting out. Let's try and actually plot the first 0.1 second, the second 0.2 seconds, the third 0.3 seconds, etc. So I think an easy way to do that would be introduce another library. So import time. The time is the Python standard library for all time-related functions. And it allows us to do something called time.time, which will return a value. It won't necessarily be near zero. It'll be, I can't actually remember where the definition of where the start point for this time is. But this time increments in real time. 1 second later, this time.time value should be exactly one bigger. That allows us to basically time ourselves. And let's just add in a few variables here. So t naught is the time now. So as soon as I'm ready to basically start plotting, or as I'm actually in this script, I'm going to take that value with whatever time returns and say that's t naught. So that's the start time. I'm going to create another value called t, which is for all intents and purposes, this is also going to be t naught in this particular instance. Or we can do another time.time because some time might pass between these calls. And then t next. So what's t next? T next is saying that the next value, the next time point that needs to be shown on the plot is going to be 1 divided by the FPS later. Okay, what does that mean? So the FPS is 10. Okay, let's say that the current time is 0 seconds. It's saying that when the time reaches 0.1 seconds, you need to plot basically. You need to plot the first 0.1 seconds of the string. We're going to use that as some sort of timer. Inside the update function, we're going to declare 2 global variables. Now, people tend not to like global variables, but I can't think of another way to do this other than overloading this function with a lambda function, which I think is probably a bit out of scope for this video. So instead we'll just call a global function. So what that does, it says, okay, these t and t naught does not exist within this function. Look elsewhere for these variables. In the first place it'll look is a script. And it'll say, okay, I found a t and a t naught here. So it'll pull those from the ether. And then we're going to want something like while time. We can't just get rid of this t naught. So t, remember, so t is a variable that we control. It just happens to be at the minute the time that the simulation was started. So it's saying while the time that the simulation was started is less than the current time, so the actual real time, start incrementing the string. So I'm going to increment the string by dt, then I'm going to say t plus equals dt. It's basically saying, so for example, if this variable t was 0, it's basically saying we've simulated nothing to do with the string, and the real time is 1 second. Basically saying keep incrementing the string by dt. Remember, dt has to be small enough that we don't have numerical errors until the current simulated time matches the real time or is slightly greater than it. And then in that case, you can continue. So this should now start plotting it in real time. If we give this a little run, you can see it is faster now. And then if we go ahead and change the speed now, change it to 30, the actual simulation should be running faster as well. So it's both in real time, a real time simulation, which we can see, and we can just do something crazy. But let's change the speed to say 1,000. What's going to happen is we're not going to see anything, or it's going to go crazy. Change it even more. There we are. It's not going to show anything. So what's happening here is it's trying to get C is so great that dt is now really small, so I can only take very, very, very small time steps. So if I quickly close that out, yeah, crashed. Good. I can only take very, very small time steps, which I'm not going to be able to see. Okay, so whatever. So the time steps are very, very small. And remember, I'm trying to plot this in real time. So what it's saying is that there's not enough time in real time to actually be able to do enough increments to get to the point where it needs to be. So this always lags behind. So it can never do this quick enough so that this t exceeds the real time. So we can't have time, we can't have this too high. So let's go back to 30. Plot it again. So I'm not a big fan of how janky this animation looks. I'm going to change the FPS. Let's try 30. Now with matplotlib, it's 30 FPS might be okay for most machines with something this simple. If I typed in something like 200 here, I'm not going to see 200 FPS. Matplotlib is not a high-speed plotting library, but 30 should be okay for this sort of simulation for most people. And you can see we get a much smoother looking plot, and it's showing pretty much what we saw in the video with the guitar. So let's go ahead and change some other things. So rather than have 128 points along the string, let's try 156. Should hopefully make it a bit nicer. Okay. And now let's start trying to understand what's actually happening. Now we've got a nice animation, we can actually start to maybe learn a bit. So obviously, as I said before, the wave equation's not a nice equation. It looks nasty. It doesn't really tell you much. You can sort of glean that, okay, where the curvature of the string is high, okay, where the curvature is high, so where, not straight lines, so where there's something with a curve is high, then that particular point is going to change a lot in time in such a way as to decrease the curvature. Or not necessarily decrease the curvature, but it's basically going to oscillate. It's going to oscillate. That's what's called the wave equation. It's an oscillatory phenomena. Kind of makes sense, but you don't really get any other information than that. So let's go ahead, change the speed to 1 on the simulation again. Let's have a look. So where that sharp point was at the top, we can actually see that it started to spread out from there. So not this straight line isn't changing, so there's no curvature. Straight line does not have curvature. Remember, second differential is curvature. So that straight line is not changing. But where the little plucked part was at the top, you see that's high curvature, because even though it's where two straight lines intersect, that has a second differential, because it's, if you think about what the second differential of that is, it's some discontinuous jump between two values, so a positive gradient and a negative gradient. So that has curvature because it has a value associated with it. And what's interesting is that because you have this discontinuity, so basically you have positive gradient and a negative gradient, you've got a discontinuity. So that's still registering as curvature, the difference between them. But that difference is very, very high because there's virtually no space where it's happening. It's a very small dx. And then there's a big gap as to what it jumps. So what you end up with is you end up starting getting these little wiggles, and that's because the curvature is so large that you start running into problems with your numerical simulation. You can't resolve some of those frequencies, some of those spatial frequencies. So you end up getting these little wiggles appearing because of the nature of this discontinuity. And we can sort of see that. So if I get rid of this simulation and we put in another initial condition, so let's go something like, so rather than have this pluck string, let's say y equals d0 times numpy.sine 2 times numpy.pi times, and let's do just the one spatial frequency. So let's do x minus 1 minus x0 times x. Have a quick plot of that. Yeah, so we've created our little sine wave. Let's make it a little bit faster. But what we can see is that when we do this sine wave, we don't have these little extra wiggles because this sine wave is very pure. It's basically one frequency and it's well resolved within our simulation. There's no discontinuity or there's no large jump between the values. So we're not going to end up with these little wiggly artifacts. And it also shows perhaps a result more familiar with the wave equation. You know, if you've got a string, you pluck it at certain harmonics, the wave will just oscillate backwards and forwards. And we can start to see some other things that may be a bit more interesting, is that where there's obviously high curvature, which are at the peaks of the sine wave, that causes a larger movement in time. So basically an acceleration in time is caused by the curvature of the string. So the string is nice and curved here, so it really wants to start going, so it starts to accelerate. And then even while it's flat, it's still moving because obviously acceleration is the derivative of speed. So accelerated to a particular speed. So even though now there's no curvature and the string is flat, the string still keeps moving because of its velocity. That velocity causes it to bend into the other direction, so to the minus y direction, which then causes another lot of curvature, which then which accelerates it backwards, slows it down, and accelerates it backwards. You also see that at the beginning here, in the middle where there's the first node, and in the end where it's also clamped, there is no displacement. So even though the line going through it is changing, the actual point itself is not changing whatsoever. So that part of the string is stationary. So this is a standing wave on a string basically, but it allows you to see over time what's happening. And remember, we've just derived this from the wave equation. We've not solved the wave equation, got the analytical expression for cosine, sine, etc. So normally what we do in undergraduate physics is you would do something like that. You would say, oh, let's look at our boundary conditions. This is the wave equation. Let's try a solution of sine. Let's try a solution of cosine. That gives you a solution that's valid on the string, and then you can always get the time expression from that. Obviously you can't see it without animating it. But then what's nice about doing a simulation like this is that, again, as we did at the beginning, we can always put in some strange initial conditions. So, you know, when you're solving the wave equation in undergraduate physics, you don't solve it for sort of a plucked string. You'd normally solve it in terms of sines, cosines, get your Fourier series, add up all your terms to approximate your string, your pluck string, and then you'd still have information about how it evolves in time without actually being able to animate it. So I think this is really nice. And again, just going back, so what I'll do, I might put the other video inside here, and then we can just have a look at the two videos side by side. You can see how one evolves compared to the other. As you pluck it, travels down the length of the string in the same shape, and then is reflected backwards. I do think this is really nice. It really shows you gain a much deeper understanding of the actual physics involved. If you take the equation, solve it, and then you can start doing interesting things. You can also do something interesting like, why don't we pluck it in the middle rather than at the end? You get something maybe you'd be a bit more familiar with, but still it's not that intuitive in my opinion. It doesn't just move. It doesn't move as you'd expect, like a triangle up and down. It sort of ripples in on itself, which I think is very interesting. So yeah, so I think we've done quite well to explain a few things there. What we could do now is you could just go through and tidy up the plot. So let's go ahead and change some things. I'm a big fan of making it look a bit more like a string. So obviously at the minute, the scales are quite different. It's 100 on the X and only 0.2 on the Y in terms of extent. Let's make that a little bit more string-like. I'm not going for the real proportions because a ratio of 100 to 0.1 is 1,000. Well, 100.2, 500. So that's quite an extreme ratio. It'd be a bit weird to see, but typically when you have these strings and wave equations, we always talk about small displacements because things like a string, if you displace it too much, the equation doesn't hold. You start changing the tension and things like that. It no longer strictly becomes a one-dimensional string. So if I just go ahead and copy some code over, so let's find a nice bit of code so we can make the plot probably a bit bigger. So there's a thing in matplotlib called rc params. So you can do plot.rc params. They're basically default parameters. And then we're going to change the fig size. So the default fig size is going to be 16 by 8, so 16 inch by 8 inch. And we'll look at that. It goes nice and big. Let's do 4 instead. We can also do things like plt.rc params. I remember what this is. Font dot size 16. That should change the font so these labels are nice and big. Speaking of labels, let's add in some labels. So let's add in x.set. Let's do x label. Let's just call it x. Easiest way. Let's do y label equals displacement. Displacement. Plot that. We're going to have a little trouble seeing that. You see it's cropped off the x a bit. We can sort that out. You do big.height layout. Should work. There we are. So it's moved everything in. So it's looking a bit more string-like. Let's try grid. Try grid. X.grid. We'll create a grid. That grid's quite intrusive. I think you can do alpha equals 0.2. Made the grid a bit too transparent. Don't know if this will come up well on over a YouTube video. But that's the grid. So you can see maybe a bit more. But I'd really like a center line just showing where the original center was of the string. That's very easy to do. We can just do x.x h line. So axis horizontal line, and you just give it y equals 0 value. Let's give it an alpha 0.23, and let's give it a color black. There we are. I'm going to get rid of the grid. I don't like the grid. Doesn't look very nice. Even that horizontal line's looking a bit dire. So let's do line style equals, let's say, dash dot style. Maybe it looks a bit better. I also don't like how the axes go 0 to 100 and then add a bit on. So we can manually come down and say x.set underscore xlim. Then we get some x limits, so let's just do x, the first value of x and the last value of x. Set those as our limits. There we are. So now we're seeing something a bit more clear, which I think is really nice. So we end up creating some nice plots of a string being plucked. And again, this is a real physical thing. So just by taking the equation, applying some finite difference, using some free software, a bit of Python, all the free stuff associated with that, we can actually start to visualize that. You can really appreciate how waves move. Like for me, when I first saw the video of the guitar string being plucked, it was just amazing. Like you just knowing the equation, I thought I knew waves, and then just knowing the equations just obviously isn't enough to know what happens. Like I wouldn't have guessed that that's what would happen, and then to actually see it is just unbelievable. So yeah, so I think this is really nice just to be able to see what happens with certain things. Like you take your physical equation, simulate it, you know, you see the standard results. And obviously a lot of time in lectures and things and notebooks, you don't actually see what happens over time. Like you'll see the sine waves, oh, it's a standing wave, and it'll just outline the magnitude of the wave. You're not actually seeing how it evolves in time. And I mean, one thing that's interesting, let's just go back to the standing wave, is that obviously they show you the standing wave, which is obviously the sine or cosine wave, but like you sometimes forget that at some point the entire wave is flat, the entire string is flat, and then it moves out again, and then it's flat, and then it moves up again, and it comes back down, and then it's flat. You sort of forget that. You sort of don't appreciate that as much when you just see a drawing of it. So I think it's really useful to just sit down with these equations and just basically do the transients. Any equation that you learn in physics or engineering, you should just sit down and look at what the transients do, because the transient stuff is the most interesting point, the most interesting part to a lot of these equations, but it's the hardest thing to do in terms of on a blackboard, for example, or just in a PDF. You need to actually be able to simulate these things. And so I think Python's quite good because it just has all the tools you can use to actually be able to do these basic simulations. And even though it's a basic simulation, I think it's really nice that we've actually been able to understand something quite complicated. So this like plucked string and how it travels, it's just really nice to see. And then when someone was fortunate enough to have a high-speed camera and actually film it, then that really helps as well. It helps us understand that and see that. So yeah, I hope you've enjoyed this video, and I think that's where I'll leave it. If I would come back to this, I would probably add a Fourier transform of the string itself, because the Fourier transform in space does the same thing. Not the same thing. It has the same sort of behavior as the actual displacement of the string. So it's a Fourier transform, but then it periodically drops to 0 where there's nothing, because obviously when the string is flat, there's nothing. And then it oscillates between a couple of states, and then that's different to the Fourier transform you'd probably be used to seeing, where you take a single point on the string, because obviously this point on the string here is, let's take here, is not moving at the minute. And then when the reflected wave comes back, it starts to move, and then it stops moving. So if you were to plot that, you'd get something where it's not moving, flat, and then it starts to move. You get some sort of square wave with like trapezoidal edges. So the Fourier transform of that is quite interesting. But obviously the Fourier transform of the entire thing changes as the wave moves. It's actually really nice to see. So I think that's what I'd do if I came back to this video. But yeah, that's where I'll leave this video. It's been quite long, but thanks for watching. So yeah. Ciao, ciao.